go back to sharing again. All right. All right. So again, definition: an interaction between two different objects that results in a push or pull is a force. An object cannot exert a force on itself. And Mr. P's definition is a force is an ability to cause a change in state of motion of an object. It doesn't mean it's always going to cause one. It just means it has the ability to cause that. Now, we can break forces down into several categories. Two broad categories that we can break it down into are contact forces and long range forces. Contact forces can be a push, a pull, friction, tension. I think that may be the only one. I'm going to say normal, which we will talk about. And then long range forces would be gravity, electromagnetism, which really encompasses both magnetism and electrostatic forces. So I'm going to leave it there. We won't talk about this much until the very end of the year. Now, I'm going to use these abbreviations. Sometimes you're going to see slightly different abbreviations, but this is what I like. F sub F stands for friction. And friction is parallel to the direction. Sorry, I'm going to say parallel to the surface. The object is sliding on, and opposite the direction of motion. And there are two types of friction. There is static friction, which is sometimes abbreviated as FSF. And I'm going to make that small. Sometimes I'm going to make it small. Can everybody see that okay? Okay. All right. And that's when the object is not moving. I'm going to make that a little bit bigger. And then there's something called kinetic friction. Anytime you see kinetic, that means when the object is moving. Now, if you've ever tried to move furniture, like move a desk, you've probably experienced this. It is more difficult to get the object moving than it is to keep it moving, because friction is largest when it's in static. So I'm going to switch over to my camera and demonstrate this a little bit. So I'm going to push on this, and I am exerting a force on this box and weight system. I am absolutely exerting a force. You can see evidence of that. The reason this is not moving, it's continuing to maintain its state of motion, is because there must be a force pushing against me. If I exert a force on something and it doesn't move, the only reason it maintains its state of motion is it must be balanced out by another force. So absolutely, there is static friction right now because it is not moving. If I continue to push harder, I can get it to move. However, when I first push, and you can see this by the box, when I'm first getting it going, there's a bigger deformation, a bigger change in the box than when I maintain it going. It's maybe hard to see a little bit here, but it is harder to get it going than it is to keep it moving. So static friction is always going to be greater than kinetic friction, but there is kinetic friction. If you move a desk, if I move this, I still am being counteracted by a friction force this way. So there is kinetic friction. But I'm going to go back to the notes and add that. And this is abbreviated as FKF, or just FK sometimes. I've seen it. And it just means kinetic friction. And as I said, it's harder to get a desk moving than it is to keep it moving. So F static friction is greater than F kinetic friction. I just want to point that out too. And at this point, I've talked for a little bit. I'll ask, are there any questions thus far? Okay. Then I'm going to keep on keeping on. The next one, FT, is tension. Maybe I'll even make it red so everybody can see it better. Make all of these nice red. So these are force of tension is a force along a string-like object. Oops, some people got dropped. So, and I'm always going to say, it's always collinear with the string, meaning it's always along the line of a string. I'm going to show you examples of a tension force after this. And it's also important to note that tension is the same everywhere in the string. I'm going to say or rope or chain. Those are good approximations of a string as well. And if it goes over a pulley, and we'll talk about this later, a pulley only changes the direction of the force. Make this red. Maybe a little bigger. Pulley only changes the direction of the force. It does not change the magnitude of the force. So to demonstrate this a little bit, I'm just going to do, I'll switch back here. I've got a string. I've got a mass on a string. It currently is not changing its motion. If I want it to change its motion, I give it a tension force. Now, if I pull it here, or if I pull it here, or if I pull it out here, even off screen, the tension is the same throughout the whole thing. Same everywhere. I do not have to add an additional force because I'm further away. I don't have to add less force because I'm closer, or vice versa. It's the same the entire time. That's the tension force. All right. Now, moving on to normal force. Normal force is the reason that you are not in the center of the earth right now. As I said, in order to keep an object from changing its state of motion, forces must be balanced. If you want you to stay constantly moving, or if you want to stay in your constant state of motion, forces must be balanced. Now, this tape dispenser, whether you can see it or not, has a force on it. The force is, and I'm not entirely sure why it won't focus on it, but the force is, maybe I'll even lift it up. No, leave it there, is gravity, right? But it is not being accelerated towards the Earth, even though gravity is acting on it. So there must be a force from my desk pushing up on this tape dispenser. That's the only reason why it is not accelerating down towards the Earth, is because there's a balancing force from the surface acting up. It's called the normal force. And a normal force is force from a surface. It always is perpendicular to the surface, causing it. That's a normal force. And then FG, you are likely familiar with. It is gravity. It is the reason why people get hurt when they're up on the roof. It's also a pretty good force. Although admittedly, it's a weak force, and we're going to talk about that later. And on Earth, gravity is always straight down. This may be intuitive, but it's important to note. It's going to help us solve problems later. Thinking about like surfaces and things like that, and angles and ramps. A lot of people want to put gravity in the wrong direction. Gravity is always straight down. So those are the types of forces that I'm going to talk about. Oh, I've got a question. What question do we have? No. And there shouldn't be. I think I've meant to delete all of them. No, all we're doing is through worksheet 1. So all this extra stuff you do not need to worry about. And really, I don't even know how much time we're going to have to work on worksheet 1. We're going to do what we can. It's just practicing. We might get to work on it as a group tomorrow. We'll see how it goes. So units of force. The SI unit is newtons. With an abbreviation of N. Pounds is also a unit. And a good conversion factor is 1 pound equals 4.4 newtons. And 1 newton equals 1 kilogram meter per second squared. That's what it's defined as. All right. Any questions? Ooh, on the type of force?
Could you just scroll down a little bit?
I'd love to. Is that better?
Yeah, thank you.
No problem. Because now I'm going to give you the rules for free body diagrams. And admittedly, there are several, but you will find that as you practice this, it becomes much more natural for you to do it. And there are even some parts that we will not do 100% of the time. But to do a perfect free body diagram or force diagram, this is what you will do. So I will give you the rules, and then we will practice using them. So the first thing that you need to do when you want to write out a force diagram or a free body diagram is identify your system. Then, if the object is touching a surface, draw the surface using a dashed line. And I want to say I didn't invent these. This is something that physicists have agreed upon. I may be making them more explicit than others do, but this is a universal physics system. represent the object with a dot, represent all forces acting on the object using vectors, which we represent with arrows. All forces are drawn from the dot, not going into the dot. They must be going from the dot. Draw force vectors, again, arrows, proportional to the size of the force. If it's a really big force, then you would draw a really big arrow. If it's a really small force, you would draw a small arrow. Use on, by notation. I really want us to practice this at the beginning. We won't do it forever, but it's really good to note because it gets a little tricky. And you're making sure that you're getting all the forces acting on it and none of the forces that are not acting on your system. 8 is break vectors into X and Y components if you need to. 9 is indicate which forces have equal magnitude. And then finally, write a net force equation for X and Y directions. So if it's moving in more than one dimension, you will, magnitude, you will need to make 2 equations. If it's only moving in one, you'll only need to make 1. Okay. So those are the rules, and I'll give you a little bit of time to get those all down. And then we're going to practice using them on worksheet 1. And I'm actually going to start working on paper. You can actually do a drawing right there, but I think it's just a little bit easier to use paper. So I'm going to. So a little bit more time. In fact, can I get everybody to drop in the chat done when they're done? I don't want to leave people behind. Okay, we've got 8 of you. I'd like to get as many possible. I want to at least get through this first example. And again, with repetition, this gets much faster. But I want to make sure we start solid here. FBDs are really an important tool that you're going to use for a long time. Okay, getting a lot of done. Just want to make sure that there's, give you maybe 30 more seconds, and then I'm going to start going through these. Okay. All right. So I'm gonna rotate and maybe focus a little bit. bring it down. All right. So here's our problem. A box sits motionless on the floor. And I want to draw an FBD, a free body diagram or a force diagram for this scenario. So first step is to define your system. The system is the box, right? This may seem like, why are we doing this? But in reality, the more careful you can be, the better and happier you're going to be. So system is the box. Second step, if the object is touching the surface, draw a surface. Got a surface. Got that dashed line. Okay. And then 3 is represent the object with a dot. Here's our dot. Represent all forces acting on the object using vectors. All right. So I know it is something that has matter. I know you can imply or you can infer that it's on Earth. So it is going to have the force of gravity acting on it. And it's acting on the box. And I'm drawing it from the dot. It's acting on the box by Earth. These are the two objects that are interacting, causing this force to happen. Now, it is not falling towards Earth, so there must be another force acting on it. And that is the normal force. That is on the box by the floor. I've drawn them proportional to one another. If the object is not moving, it should be, they should be equal in size, in magnitude. We don't need to break this into X and Y coordinates. So I'm just going to leave it right here. I'm going to indicate which forces have an equal magnitude. You do that with this. These lines mean they are equal. And then finally, the net force equation, you'll write like this. Net force means sum of the forces this is moving up and down. Gravity moves down, so it's the forces in the y direction. This means sigma means sum of. And all the forces in the y direction, I'm going to call up positive. So because of that, I'm going to make my normal force the positive force. Since this means sum of, we're going to add the next force. However, it's in the opposite direction. So I'm going to call it a negative force, just like a negative acceleration. And if there's no movement, no change in the state of motion, they're going to equal 0. So the normal force plus gravity, which is in the negative direction, equals 0. We could even rewrite this, since this is equal to 0, and say we add the force of gravity to both sides. Get our normal force equals our force of gravity. And really, that's it. That's an FBD. So I talked a lot. I don't know that, you know what I'd like you to do? Why don't you just finish 1 through 3 So I would like you to finish, I guess, just 2 and 3. Come to class tomorrow with 2 and 3 done, and we will start on 4. There's a little trick to 4 that is just going to make your life a little bit easier, but do 2 and 3 by tomorrow. Are there any other questions? I'll be here for a little while longer. Any questions about why I did what I did? If not, class is officially done. So you can go forth, work on 2 and 3, and I will see you tomorrow.